Would you also like to record?
Yeah, sure.
Yeah, so I can kind of allow you. Okay. Also, I wanted to mention that Abhay Srivastav would be the tutor for this course, and I have already informed him about the schedule and the place where I keep the lecture notes. So, all those who are crediting the course, please get in touch with him. So, as of now, Kaustubh and Harshita are crediting the course, right?
Yeah, I
Yes,
think
boss.
yeah.
Yeah. So if anybody else is also crediting, please inform him, because he'll have to kind of uh, grade home assignments and keep track of all that stuff and so on. Okay. Okay. So coming back to what we were doing last time. Uh, so it turns out that uh, our estimate for E going as 7 n to the 7 by 5 is not really kind of something that happens physically. In fact, if you look at Thomas Fermi model in atomic physics, you find that delta E is actually proportional to n to the 2/3. Okay. Now, of course, Thomas Fermi approximation is also very crude approximation. Only gives leading order results correct. It needs to be corrected further, as we learn in atomic physics soon. But nevertheless, this is a kind of behavior it shows, which is certainly milder than this factor. Remember, if the power was larger than 1, then we would have had trouble. The power is actually smaller than 1. And therefore, the delta E is not really growing as fast as these kind of factors that we talked about in the last lecture. Part of this sub kind of sub-integer behavior of delta E is related to Pauli exclusion principle, although this relation is not so direct thing. Okay. This additional thing that we notice in atomic physics, which was kind of discounted when we did this crude computation, and that is that in atomic physics, we see that there are very few electrons in the orbit which are close to the nucleus. Okay. For example, if you look at hydrogen atom problem, then the closest orbit to the nucleus has a principal quantum number 1, and the principal quantum number 1 orbit has only L is equal to 0, and L equals 0 can only accommodate 2 particles if they have spin. Okay. uh, so uh, but as you start going to higher and higher principal quantum numbers, then you would have more and more L values allowed and therefore larger number of particles. Okay, so this is what we see in atomic physics, even in hydrogen atom problem, and similar behavior we see when we look at the periodic table also. Okay, so as we go away from the nucleus, then we can actually accommodate more and more electrons in the orbits. Now, this seems a bit counterintuitive, because you have an attractive interaction between nucleus and electron, and you would have expected that if the interaction is attractive, then the charged particle would want to reside closer to the nucleus. Electron would choose to live closer to the nucleus than kind of far away. Okay. Now, this intuition, of course, would have worked quite well had the electrons been bosons. Okay, and that is because if the electrons were bosons, there is no limit on how many electrons could occupy a given energy state. Okay, so therefore, in spite of solving the hydrogen atom problem, now recall that when you solve hydrogen atom problem in quantum mechanics, you do not really use the fact that electron has a Pauli exclusion principle until you take the spin degree of freedom into account. So when you write down the spectrum to be some z squared e to the 4m upon some h bar squared n squared or some such thing, maybe 2 h bar squared n squared, I don't know. But when you write down something like that, you have not used the fact that electrons were fermionic objects. Okay. So imagine solving quantum mechanics problem in that fashion and say that, like, okay, instead of fermions, I populate this atom by putting bosons there. And the thing is that, like, if you try to do that, then because there is no exclusion principle, the kind of a principle that fermions have to satisfy, all bosons would probably try to go and stay in the ground state, simply because that is the one which would lower the energy of the system. Okay. Now, of course, if you are looking at the system at finite temperature, then there are some thermal fluctuations, and therefore some electrons would be in some few excited states. Uh, I shouldn't use the word electrons, but, like, analogs of bosonic analogs of electrons would be in some few excited states. But barring that, most of the ferros would probably try to be in the ground state. And in that case, actual size of the atom would be really small. Okay, because I try imagining something like cesium, which has electron in principal quantum number 6. So 6x1 is the outermost electron, which gives cesium atom a pretty large size, simply because this orbital is kind way out of kind of out of I mean, from the nucleus, and compared to, say, size of hydrogen, it is quite a large atom. In fact, uh, the energy required to remove that 6s1 electron from cesium is much less than the energy required to remove one electron from hydrogen atom. Okay, so in that sense, you can easily imagine that that electron would be much less bound, much more weakly bound to the nucleus than hydrogen atom electron. Okay, so but had the charged particle been bosonic, it would have been all close to the ground state, and therefore the atom would have been pretty small. And in that case, again, the two systems, if you bring them together, the change in energy would be comparable to the energy of the original system. Okay. Okay. Uh, so yeah, so this is something, of course, we know that the electrons are fermions and obey Pauli exclusion principle, and therefore, if you make any choice of quantum specific choice of quantum numbers, only one electron can occupy it in a given atom. So therefore, that is the reason why there is a large spread and large size of the atom. Okay, so uh, so we can kind of give an explanation as to why atoms have finite sizes, and that is all attributed to fermionic nature of these particles. Okay, it's also the reason why the densities of matter that you see is finite. Uh, the reason is again the same, because if these particles were bosonic, then the atoms would have been very small, and these atoms, if they are occupying the lattice sites, those lattices also would be very small. Okay, and therefore the density of materials would have been much larger than what you see in real life. Okay, and the final thing is, of course, that because of these things, that the atoms have larger size, systems have lower densities, we also find that we can take thermodynamic limit of this kind of system than a system which is consisting of purely bosonic material. Okay. Okay, so I'll just state this thing without any proof, but, like, you can check this in some atomic physics systems, or you know there are other systems like astrophysical systems also, in which this kind of study has been done, that if you take Pauli exclusion principle into account, then you can find that energy spectrum actually grows as z to the 7 by 3 and not as z cube that we had computed using our crude computation. And similarly, the size of the atom is actually proportional to z to the minus 1/3 and not proportional to 1 over z. Okay, now this is like for example, if you are trying to study, say, neutron stars, okay, then in that case you could also ask the question that, like, if the system is made up of neutrons, and if there is a strong interaction uh, force, which is the only active force there and which is attractive, why doesn't the neutron star collapse? Okay, And one of the reasons why it cannot collapse is because neutrons are fermions, and therefore there is a pressure due to Pauli exclusion principle. And until it overcomes the Pauli pressure, the neutron star cannot collapse. Okay. Now, of course, if the neutron star becomes larger than a certain size, like for example, if it crosses certain solar masses, for example, if it is 1.4 solar masses, which is the Chandrasekhar limit, if it crosses that, then the neutron star would form. But if it crosses about 3 solar masses, then even this object would collapse into a black hole. Okay, that is a point at which the Pauli exclusion pressure also would be overcome by a gravitational field. Okay, but purely attractive force due to gravity and strong interaction can be balanced by Pauli pressure, and in that case also you would find that the neutron star does not uh, collapse into a black hole um, because of Pauli pressure. Okay, so coming back to what we were doing, we want to study critical phenomena, and so we will try to understand certain aspects of this uh, setup before we embark on any specific model. And at least my today's plan is to talk about these aspects first, and hopefully in the next class we will really be looking at the model. Okay, but if you happen to actually uh, make fast progress, then we could start the model to itself. Okay. Okay, so coming back to critical phenomena, suppose you want to study how iron undergoes a transition from a paramagnetic state to a ferromagnetic state. Okay, suppose you want to do that. Okay, so let me first define these words. Okay, so a material is called paramagnet if it is attracted by a strong magnet. Okay, so that is what when we call paramagnet. Now, this is something we know in ordinary life. If you have a magnet and if you bring it close to the iron, iron will get attracted and stick to the magnet. Okay, fine. So that is one property which is called paramagnet. Okay, the other property, which is the other word which we have used, is ferromagnet. And ferromagnet is a material which has large magnetic moment. Okay, so for example, the magnet itself is a ferromagnetic object because it has a large magnetic moment, and it can attract objects which have paramagnetic behavior. Okay, now iron itself can undergo a transition from paramagnet to ferromagnet. Okay, now this is also something which is common knowledge in the sense that you can convert ordinary iron piece into a magnet by kind of applying, say, magnetic field, or by uh, actually just keeping it in the vicinity of a magnet for long enough. Okay, so that uh, kind of it also develops kind of ferromagnetic behavior. Okay, we will see why such a thing would happen at room temperatures for iron without doing too much work. Okay, but these are the definitions of these words. We will try to understand this little more mathematically later. Okay, so what we want to do is to actually study this system by studying large systems. Okay, so for that we would try to take thermodynamic limit of the system. Okay, but again, thermodynamic limit is purely a mathematical thing to do. As I said last time, the thermodynamic limit corresponds to taking total number of particles in the system to infinity. Okay, along with, of course, making the volume of the system infinite, but holding the density fixed and all that stuff. Okay, but this is not what we would really do. Okay, now of course I am taking a specific example which is not what you would really call even a large system, but nevertheless, just to get an idea of the scale of the system, let us look at a cube of iron. Okay, with each side of length 2 centimeters. Okay, so that is a pretty small object actually, if you can think about kind of that size. It's like not even an inch in all direction. It's just about uh, 2 centimeters. Okay. If you look at the object of that size, then it would have about Avogadro number of iron atoms in it. Okay, in fact, the number would be a little larger than Avogadro number, but okay, uh, definitely about Avogadro number of iron atoms. Okay, now Avogadro number is quite a big number. It's like of the order of 10 to the 23, but it is still much, much smaller than infinity. So in that sense, you know, if you want to take a system which is 2 centimeter by 2 centimeter by 2 centimeter, it would be difficult to say that, like, you know, you are actually talking about thermodynamic limit of the system. Okay. So, uh, but nevertheless, when you are trying to study a system, you would want to ask a question that if I look at a system of this size, maybe not 2 centimeter by 2 centimeter kind of object, but like imagine, like, you know, a meter by meter by meter, like, you know, a cubic, 1 cubic meter kind of object. Okay. Now, 1 cubic meter will make this number go from 10 to the 23 to maybe 10 to the 35 or something, you know. But that doesn't make much of a difference because infinity is like way out anyway. Okay, but nevertheless, you know, we want to ask a question that, like, you know, how does the system scale as you scale up the numbers? Okay, if we understand how that happens, then in n going to infinity limit, we would have some picture as to how the system would behave. Okay, now this thing is done in the following way, that you think of a system of certain size and you ask a question that how are quantities inside the system correlated. For example, imagine that, like, you know, this iron cube that we are looking at some lattice point we have iron and we kind of disturb that uh, iron atom. Okay, and you want to ask that if you disturb that iron atom, that disturbance would affect its neighbors, and the disturbance experienced by neighbor will affect their neighbors, and so on. Okay, but as as it progresses, at some point this effect will die out. Okay, if it doesn't die out, then the system would actually have a chaotic behavior, and maybe the iron cube would probably just blast and kind of break into pieces. Okay, typically such a thing doesn't happen. Okay, this effect dies out at some point, and after that you can happily imagine that all other iron atoms at other lattice sites further away would not even experience any disturbance. Okay, the length over which a significant amount of disturbance would be experienced is what we call a correlation length of the system. Okay, so if these correlations are much larger than the lattice size, okay, now typical lattice size for such materials is of the order of a few angstrom. Okay, 1 angstrom to 5 angstrom to maximally 10 angstrom. Okay, uh, 10 angstrom is really large size lattice. Doesn't really happen in, like, for example, in case of iron, it is probably 2.3 or 2.4 angstrom in each direction. Okay, but uh, you may allow certain cases in which the distances are large. Okay, but if you're thinking of correlations which are of the order of, say, micrometers, okay, or of the order of like tens of micrometers, okay, then uh, like 10 micrometers is about 5 orders of magnitude compared to the angstrom. Okay, so 10 micrometers is like 10 to the minus 5 meters, and an angstrom is about 10 to the minus 10 meters. Okay, so therefore the correlation, which is of the order of 10 micrometers, okay, is small with respect to the original system, which is 2 centimeter. So it is like, you know, 3-4 orders of magnitude smaller than the original system. Okay, but it is about 5 orders of magnitude larger than the lattice size. Okay, if you see a system like this, behavior like this, then you could say that, like, you know, you can consider thermodynamic limit of this system, simply because over the size of the total size of the system, the correlations would kind of have like effects which, like, 10 to the 3, 10 to the 4 correlations could simultaneously exist without overlap in a total system. Okay, because every correlation is of the order of 10 microns, and to reach about a centimeter, it would require kind of going up by 4 or 3 orders of magnitude. Okay, so about 1,000 such correlations could exist in the system without them talking to each other. Okay, and each such correlation is way larger than the basic unit which defines the lattice. Okay, then you could say that with respect to these correlations, the system size is pretty large, and you can imagine that you have taken thermodynamic limit. Okay, so thermodynamic limit is defined in this fashion in all these systems, and then you of course scale it up and say that, like, if I scale up the system, how does these results scale, and then take the mathematical limit of.
So, do we really need the first of these points that the correlation should be much larger than the lattice length?
Well, we don't need it right now, but when we'll look to study critical phenomena, then we will need it, because usually what happens is that in ordinary systems the correlations fall off exponentially fast. Okay, but in the critical phenomena they don't. Okay, so you would want the correlations to be long enough so that compared to the lattice size, it has a bigger fall-off behavior. Okay,
Okay.
so in other words, let me put it a little differently, that what we are going to do actually in reality is take this lattice model and convert that into a field theory and do a quantum field theory of that object. Okay, but to do that, you are, after doing converting that into quantum field theory, you are going to treat that as a continuum field theory. But that makes sense only if the scales over which physics is studied is much larger than the scale of the lattice, so that you can think of the space-time to be continuous. Okay, that is one reason. That is the reason why we want the correlations to be larger than the lattice size. Does that make sense?
Yeah, okay.
Okay. Okay. Fine. So we know that the lattice structure of iron is of the simple cubic form. Okay, so it's a simple cube. At every vertex of the cube, there is one iron atom sitting there. Okay, and iron has atomic number 26, and its outermost orbital configuration is 4s2 3d6. Okay, that is the structure. Of course, there are the other ones which are all completely filled shells. Uh, and so I'm not writing them, like 1s2 2s2 2p6 kind of stuff. Okay, fine. So what matters real for us, what really matters is 3d6, but I have still written down 4s2 and 3d6 for the following reason, that well, we'll see in a moment. Okay, so but the thing is that, like, by virtue of Hund's rule, remember 3D, the d orbital can take about 10 electrons. Okay, and in this particular case, only 6 electrons are occupying d orbital, and Hund's rule tells you that you occupy the states in the orbital with all spins oriented in one direction, and after you fill that, then all spins oriented in the other direction. So in other words, if you have 6 electrons, then you have 5 electrons with spin projection, say, up, and 1 electron with spin projection down. That is how the state would be occupied. Okay, so therefore there are 3 effective spins pointing in one direction. Okay, inside the iron atom. Okay, 3 or 4 maybe, sorry, 4. Okay, so this partially filled d orbital therefore has a strong magnetic moment, because there are 4 d orbital spins, 4 d orbital electrons are pointing in one direction. Okay, and the other 2 are kind of paired up. Okay, is that fine? So as a result, these 4 electrons generate a strong magnetic moment for the iron atom. Okay, now the reason why it happens this way is because, if unlike the S wave orbital, which are kind of broad wave functions, d orbital wave functions are very narrow. Okay, and because they are narrow, the electrons occupying d orbitals are actually localized. Okay, so they are not kind of, the wave functions are not spread out wave functions, And because those electrons are localized, they effectively contribute the magnetic moment generated by the spin degree of freedom of the localized electrons. Okay, and that is how iron has magnetic property. Okay, so therefore what we could do is that we could say that like this strong magnetic moment that iron atom has can be mimicked by assigning a spin degree of freedom at every lattice site in a cubic lattice. Okay, so that is what would be the way we would try to represent the iron atom sitting at every uh, vertex of the cubic lattice. Okay, now we want to study paramagnetic to ferromagnetic transition, and iron undergoes this transition from paramagnetic state to ferromagnetic state at about 1044 degree Kelvin. Okay, that is the transition temperature. Now notice that this temperature is much higher than room temperature. Okay, so in ideal situation, you would have expected that iron at room temperature would have behaved like magnet. Okay, but that's not what happened. Okay, if you try to look at iron, typically it looks like it is behaving like a paramagnet, and but it's not a in a ferromagnetic state. Okay, but as I said some time ago, that you can convert iron into a magnet by either applying magnetic field or by keeping it in the vicinity of another strong magnet, which is also like applying magnetic field really. Okay, and the reason why I said the reason why iron does not have ferromagnetic behavior in general is because inside the iron you do have ferromagnetic setup, but there are domains. There are domains of ferromagnetic. Uh, Let me say it a little differently. There are ferromagnetic domains inside the iron with the effective magnetic moment pointing in one direction. Okay, then there is another domain with effective magnetic moment pointing in some other direction, and so on. And as you kind of, if you look at the iron block, it may have like of the order of 10 to 3, 10 to the 4 such ferromagnetic domain, and each domains are effectively pointing in some direction or other. Okay, so that the vector sum of all these magnetic moments may actually turn out to be zero or very small number. Okay, if that happens, then iron itself does not behave like a magnet. Okay, but given the fact that there are ferromagnetic domains sitting inside the system, you can always try to orient those by applying magnetic field, which would kind of make the domains slowly change their direction and orient along the magnetic field. Okay, so that is the reason why without doing any hard work to convert to make it a magnet, iron can just turn into a magnet at room temperature simply because it is way below the transition temperature, and in normal circumstances you would have expected it to be in the ferromagnetic state. Okay, so our interest is not really to study system at like say room temperature, which would be about 300 degree Kelvin, but our interest is really trying to understand how the system makes transition from temperature higher than the transition temperature, which is about 1050 here, to a temperature which is lower than the transition temperature. Okay, and to be precise, we would really want to be in the close vicinity of the transition temperature itself. Okay, now uh, it may seem like okay, this is the structure that we want to study, but how do we actually study this for something like a system in of this type where we have iron cube, and you want to ask how it undergoes a paramagnetic to ferromagnetic transition. Okay, the system actually appears to be much more complicated. Okay, now until we really look at how the system is, it may not appear that the system is very complicated. Okay, so let's kind of list a few things as to what are the things that are involved which could make this system look so complicated. Okay. Okay, so as I said, there are multiple things that are happening simultaneously in that system at any at really any temperature, but in particular at close to the transition temperature. So let's look at what happens. Okay. Now, some of these things that I'm listing actually happen at arbitrary temperature, even at room temperature. Okay. But nevertheless, these facts are true even at close to transition temperature. Okay. So the first thing is that iron is a good conductor, that everybody knows. Okay. And this good conductor behavior comes from the 4s electrons. Okay. And as I said, that 4s electrons have extended wave functions. So when you actually form a lattice, then these wave functions actually spread all over and kind of become the block wave function, and they form what is called a conduction band. Okay, these conduction band electrons would of course gain significant energy if you keep the iron at 1000 degree Kelvin. Okay, because that heat bath has huge amount of energy for a conduction band electrons. Conduction band electrons could propagate quite freely because they are just some kind of almost free electrons available in the system. Okay, besides these electrons which could carry away a lot of energy in the system, you could also have significant energy stored in the lattice vibrations. Remember, lattice, simple cubic lattice, for example, is an idealization of the system, because that is how the structure would be if you look at the system at zero temperature and also ignore quantum fluctuations of the system. Okay, so let's forget about quantum fluctuation. But even at only at zero temperature, this system would be an ideal cubic lattice. Otherwise, the lattice, of course, always has some thermal fluctuations, and this temperature-induced effects are typically called phonons in the system, which are called which are lattice vibrations or quanta of lattice vibrations, and they would carry huge amount of energy. And particularly if you are at about 1000 degree Kelvin, the, the lattice vibration would have a large amount of energy stored in it. Okay. As I said, that the magnetic moment of the iron is due to the d orbital electron, and these wave functions are localized and therefore contribute to local magnetic moments. Okay. And this magnetic moment can be mimicked by saying that there is a spin degree of freedom sitting at every lattice site, and which we would treat as a quantum mechanical degree of freedom. Okay. So now, given that this spin is a degree of freedom is coming from the d electrons in the d orbital, this spin degree of freedom should really be treated as a Heisenberg spin. Okay, Heisenberg spin is of course a quantum system. The spin can take uh, any arbitrary value. In case of electron, it will take value half this thing, but its projections could be in any direction. The quantized projection in z direction is, of course, for electron will be half minus half, but for any other integers spin values, it would be all integer values allowed from largest spin to minus of the largest spin. Okay, separated by integral values. Okay, so that is a kind of system. Of course, Heisenberg spin, although z component projections are like that, x and y components are magnitudes are roughly of the same size. Okay, although average values are zero. Okay, so that is how the Heisenberg spin should be used. Okay, so that should be the correct description of the system as far as you are looking at the spin degree of freedom of this system in order to study the transition from paramagnetic to ferromagnet. Okay. Now, of course, these spins, as I said, that we should treat them as quantum mechanical degrees of freedom. They would also suffer some thermal fluctuation, because if the temperature is available, uh, thermal energy is available, that thermal energy would allow the spin to orient in any direction it wants. And that freedom is something that one should take into account while studying the spin system. Okay. Besides that, there are other issues. Like, for example, if you say that the iron cube that we are looking at is 99.9% pure. Okay. Now, 99.9% pure means there is one impurity per 1000 iron atoms. Okay, but that sounds like a very nice thing. But if you have 10 to the 23 atoms, then there are 10 to the 20 impurities. Okay, so therefore, although the impurities will be sparse, because 1 in 1000 would be an impurity, 10 to the 20 impurities is still pretty large number. Okay, these impurities could probably displace iron atom from the vertices of cube, or these impurities could sit in between the uh, lattice positions, like they could form some body center cubic structure by impurity sitting at the center of the cube, or it could sit on the face center cubic structure, and so on. They could do all kinds of things. These kind of impurities could also contribute to certain aspects, like because these impurities generate certain modification in periodic potential, because they are not iron atoms, they would have different magnetic properties, they have different Coulomb properties, and therefore the potential, local potential could be different, and some of the freely moving electrons may get trapped, and you can have a localized state because of the impurity. Okay, it can produce all kinds of such effects, and uh, that makes the system much more complicated. Okay, now clearly it would be difficult to deal with all these things at one go. We are not going to kind of solve this problem by keeping track of every such aspect, and try to see how the system is undergoing the transition. Okay, so what we need to do is to do a drastic simplification of the system and write down a model for the simplified system. Okay, so now, it is not such an easy thing to kind of do a so-called drastic simplification, and it's also not easy to kind of come up with a model which would explain this simplified system, which keeps the essential features of the original system. Okay, so that is one aspect that plays important role in modeling systems of these kind. Okay, so. Uh, so when one tries to do drastic simplification, it depends on the process of simplification that is used. What is what is the choice that one makes, uh, and what is the physics that you want to capture in the system? Okay, so like for example, in our case, we want to study paramagnetic to ferromagnetic transition, and therefore we would mostly be focusing on what happens to the magnetic moments of the iron atoms, and that is going to be our major focus. Okay, so but as I said, that the typical condensed matter systems therefore are quite dirty, because a lot of other things are also simultaneously happening, and you cannot just focus on one particular aspect and say that, like, okay, I ignore everything else and I just look at this aspect. Okay, there are some situations in which you can do that, but not always. And that is another reason, well, that is one reason why, in spite of these systems being quite dirty in kind of quotes, uh, they are therefore much more interesting systems to study, because to write down a phenomenological model to capture essential physics of the system would require a lot of intuition. Okay, much more than probably most of the other fields would require. Okay, so one needs, as I said, one needs to develop a lot of intuition to decide on which feature to focus on and which features to ignore. Now, when one says which features to ignore, one does not mean that we ignore those features completely. But when you write down a model, you focus on certain features. You write down a model which will kind of explain those features, and then you start correcting that model such that the features that you had ignored in the beginning could also be incorporated. Okay, so the evolution of a model into a theory would require it to first at least produce the features that uh, you wanted to focus on to start with, and then you convert that model into a thesis in which you propose that even the thing that you have ignored can be explained by modifying the model such that all other effects could also be explained. And then actually it becomes a theory by explicitly demonstrating that modifying the original model appropriately, you do reproduce the results that you had ignored in the first place. Okay, so just try to give I want to give one example of high TC superconductors. Okay, and this is kind of so let me say that, like, I'm not probably talking about the latest high TC superconductors, like, there was some proposal that there is something at room temperature and so on. I'm not talking about those, but there are so-called high TC superconductors which were discovered like in 1986, which was lanthanum strontium copper oxide, and then whose transition temperature was about 36 degrees Kelvin. And then there was a relative called yttrium barium copper oxide, whose transition temperature was around 87 degrees Kelvin. And then there were some additional relatives of these yttrium barium system, uh, with additional calcium being used, which pushed the transition temperature above 100 to about 125 to 130 and so on. In these systems, there is one common feature in all of them, and that was what is called a copper oxide system. Okay, and these systems were mostly layered materials. That means they were two-dimensional systems. Uh, the the typical lattice size in 2 dimensions was of the order of 3 to 4 angstrom, whereas the inter-layer distance was of the order of 12 angstrom. Okay, that is a kind of system, and this set of models, large number of them were some kind of doped copper oxide systems. There was earlier it was believed that noble metals like copper, silver, iron would not show superconductivity, and there was a elaborate explanation given as to why they wouldn't exhibit superconductivity. But later on, it turned out that copper oxide systems with certain rare earth impurities actually did show high TC superconductivity. Now, these systems are complicated in the following sense, that they are not pure copper oxide systems, but they are doped. Okay, and in fact, the undoped systems do not exhibit superconductivity at all. Okay, undoped materials are in fact antiferromagnets. Okay, now um, ferromagnetic, given the fact that superconductivity is diamagnetic, you would have expected that the magnetic materials wouldn't exhibit superconductivity. So in that sense also, it was surprised that an antiferromagnet after doping actually became superconductor. Okay, so there were lot many new things to learn when the high TC superconductivity was discovered. Okay, now the important thing about these systems when you want to try to do modeling of these systems is the following: that if you study transport properties of these materials, like for example electrical conductivity or thermal conductivity and stuff like that, then these behaviors actually show what is called a non-Fermi liquid behavior. Okay, there is a paradigm called a Fermi liquid, which was proposed by Landau. In fact, it's called Landau Fermi liquid. Was proposed by Landau in 40s, and and that explained a lot of condensed matter systems pretty well. Particularly, metallic systems were explained quite well using Landau Fermi liquid system. And uh, if you are looking at systems which kind of make transition into superconductors at low temperature, it was believed that they would have some kind of Fermi liquid behavior at transition temperature higher than TC. Okay, but these systems actually did not show those behavior as neither as a function of temperature nor as a function of any other variable like amount of doping, or if you kind of perturb this system by trying to see, say, AC conductivity as a function of the frequency of input AC current. Even that, those behaviors showed non-Fermi liquid behavior. Okay, so you would have thought that, like, okay, the system needs to be described in terms of completely new set of what are called quasi particles, and we'll have to abandon Landau's Fermi liquid theory. Okay, On the other hand, if you try to study magnetic properties of these materials and say, for example, photo emission property, there is some experiment called angle resolved photo emission. If you try to kind of look at in what direction the photon emission would happen if you impinge energy onto the superconductors, um, that kind of experiment actually shows existence of Fermi surface. Okay, so therefore the system is complicated. On one side you see that it is not a Fermi liquid, on the other side you see that there exists a Fermi surface uh, in the system. And clearly if you want to propose a model, you cannot focus only on say transport properties of the system and ignore say magnetic or photo emission properties of the system, or the other way around, that you only focus on these properties and ignore transport properties. Okay, so you need to take into account, even to start with a basic model, take into account mix of the two to be able to kind of give a reliable model which you can further correct to get other results right. Okay, so to summarize, uh, after deciding which phenomena we want to describe, we need to look at those features of the system which can affect the outcome of the model proposed to describe the system. Okay, so that is the essence of how you do modeling for such dirty systems. Okay, so dirty in the sense that, like, there exist several phenomena occurring simultaneously in the system, but you want to focus on only one of them as a primary phenomena that you want to explain first, and all other effects would be explained later. Okay, so and uh, if one believes kind of the quasi-particle paradigm, uh, which is very common in condensed matter physics, where you do the following thing, that you find the right kind of variables of the system which would give a description of the major aspect of the theory in terms of those variables which are called quasi-particles, then all other effects can be treated within perturbation theory. Okay, so just to give one example, in fact I can give a couple of examples, but uh, ordinary superconductivity, what's called a BCS superconductors, has one classic example where the quasi particles um, uh, can play important role. And so basic variables in the system are of course electrons and phonons. Okay, but in the superconducting phase, neither electron nor phonons are the right kind of variables. If you try to use those variables to write down your model, it will become too complicated a thing. What you need to do is to write down a new quasi-particle, which is a coherent state of two electrons with opposite momenta connected by a phonon. Okay, that object is called a Cooper pair, and it is this Cooper pair which undergoes superconducting transition. Okay, and it is this variable which gives the best description of superconductivity, and all other subleading or all other relatively less important phenomena are explained in terms of this Cooper pair with its coupling to various other uh, effects like magnetic field or thermal fluctuations and things like that. Okay. Similarly, in case of say quantum Hall effect, or rather maybe fractional quantum Hall effect, the original degrees of freedom are again electrons in very strong magnetic field, but it has been shown uh, by say Janendra Jain uh, that you can write down, instead of studying fermions in very strong magnetic fields, it may be much better to study what are called composite fermions in a much weaker magnetic field. And the composite fermion is a very simple idea of thinking of new quasi-particle, which is electron times certain number of magnetic flux tubes. Okay, so if you have very strong magnetic field, you can divide that large magnetic field into magnetic flux tube, which you can assign to each electron, and that composite object will be called composite fermion. Then this composite fermion sees effectively low magnetic field, and a lot of experimental data in fact agrees with this kind of behavior. For example, the orbit size in the magnetic field, uh, in strong magnetic field, electron orbit would be very small. Whereas if you try to do an experiment in if fractional quantum Hall effect, you find that the orbit is large, indicating that the actual correct quasi-particle is composite fermion. Okay, and in terms of composite fermion, the description of system becomes much simpler. Okay, so yeah, so that is the kind of idea that one wants to utilize in doing modeling of systems of this type. Okay, so now let's get back to what we wanted to do. And what we wanted to do was to focus on the magnetic properties of iron. Okay, so when we want to study magnetic properties of iron, we will therefore focus only on the d band localized magnetic moments, and we would treat those guys are localized on the lattice sides of the cubic lattice. Okay, now since we are going to focus on these d band localized magnetic moments, we will completely ignore the conduction band electrons. Okay, because conduction band electrons are not playing any important role in our description right now. Okay, as I said, that system at 1000 Kelvin would have a lot of thermal energy available, and lattice would be far from cubic lattice really. Okay, but nevertheless, we will ignore lattice vibration completely. Okay, so and this is basically just to say that the lattice vibration is not going to affect the magnetic properties in a leading way. There may be a sub-leading correction, okay, but that we can worry about later. Okay, so as you can see, we are making drastic kind of simplification. First of all, we got rid of conduction electrons, then we got rid of lattice vibration. Now we are going to get rid of Heisenberg spin also. Okay, so what we'll do is we'll replace Heisenberg spin by a classical spin which takes only two values, +1 or -1. Okay, so instead of looking at the full Heisenberg spin, we are really looking at its z component of that spin, and we'll only assign two values to that z component, and that would be +1 or -1. Okay, now this may give you an impression that actually many of these systems, I mean, in many of the magnetic systems, the conduction electrons may not be important. Okay, but that is not really the case. In fact, there are situations where the conduction electrons do contribute to the magnetic properties. In fact, magnetism due to what are called itinerant electrons is a very well studied subject and is relevant to many physically realized systems. Okay, so it is not like uh, that only localized magnetic moments is the only thing that would contribute to magnetic properties of the system. Uh, Even itinerant electrons are important. Okay, but as far as our problem is concerned, we are going to kind of not look at that setup. Okay, anybody who is interested in condensed matter physics may find this kind of magnetism discussed in probably condensed matter 2 course. Okay, quite an interesting system. In fact, is of current interest. Uh, lot of systems like there's something called colossal magnetoresistance, and then there are these heavy fermions and all. Many of them would require such itinerant behavior. Uh, okay, but I'm not an expert in it, so I will not kind of elaborate on that. Okay, so so let us denote the spin at site I by Si, giving value ±1 to that, and to help get the global magnetic moment, we will put this system into an external magnetic field. Okay, so why are we trying to do this particular stuff? Uh, the reason why we are trying to do this is exactly the reason why we want to put iron in some magnetic field to convert that into a magnet. Okay, so to put it a little differently, suppose you have spin sitting at all lattice sites, and I reduce temperature from T greater than the transition temperature to T less than transition temperature. Under this transition, the system may not get into a ferromagnetic state because you may have multiple domains or pointing in different directions, and vector sum of all these magnetic moments may be close to 0. And in that case, you actually do not see the ferromagnetic behavior of the system. On the other hand, if you start with a system which is above the transition temperature and apply magnetic field, then all the spins, because the system is paramagnetic, all the spins would tend to point in the direction of magnetic field. And as you start lowering the temperature, holding the magnetic field fixed, the system will make a transition into a ferromagnetic state with most of, if not all, most of the spins pointing in the same direction. And then it would produce a global magnet because most of the lattice sites are contributing the magnetic moment in the same direction. Okay. After you go below the transition temperature, you may safely turn the safely turn the magnetic field down to 0 and check what is the behavior of the system. Okay. Now that is the kind of setup that one is looking at. Okay. So let's try to do some simple calculation here. Okay. So since each spin can take two values, and suppose you have n lattice site in the problem, then the total number of states that you can write down is 2 to the n. Okay. Because at every site you have two possibilities. Okay. So therefore you have 2 to the n possibilities. Okay. So that many states are available. Okay. So yeah, so before I get into this, any questions about whatever I talked about, our generalities of kind of systems and how one takes make simplifications of it? In fact, like whatever I said about how one simplifies these models, this is a kind of feature that is used in almost every condensed matter setup. Okay, no matter what system you look at, you would be basically interested in trying to model the system by focusing on the dominant feature of the system. And that is one of the reasons why in condensed matter uh, field, you may find people writing down totally different looking theories simply because you look at a system which is so complicated, and you have done like about say 20 different experiments, and somebody may think that experiment 1 to 5 are important, and somebody may think that maybe 7 to 12 are important, and clearly there is no overlap between what are considered to be important experiments, and therefore different groups may come up with totally different looking models, and of course they would disagree with each other as to what is the right thing to look at. Okay, but of course uh, science progresses by having multiple ideas of this type, helping kind of synthesize the models into a better looking theory over the time. Okay. So whatever I was talking about as to what needs to be focused on is nothing special about what model that we are going to kind of uh, reduce the iron system to, but this is the kind of thing which is true in general. So therefore, I would just wanted to know if anybody has any questions. Okay, so maybe I can get back to what we were doing. So the simplest Hamiltonian that we could write down, given the fact that we have some external magnetic field acting on the system, is to say that every spin sitting at the lattice side interacts only with this external magnetic field. Okay, and therefore your Hamiltonian is H is equal to HI SI, where SI is spin at ith side and HI is the magnetic field felt at ith side. Okay. Now there is no reason why the external magnetic field has to be uniform all the time. Okay. Uniform external magnetic field is a simple and nice object to study, but you could have space varying magnetic field, you may have time varying magnetic field, you can have all kinds of possibilities. Okay, so here's a Hamiltonian where you have kind of interaction of external magnetic field with the individual spin. The minus sign is just to kind of indicate that if the spin points in the direction of magnet external magnetic field, then it would lower energy. Okay, so that is the kind of behavior you would call paramagnetic, because paramagnetic systems are the systems which are attracted by the towards the magnetic field. Okay, fine. So let us try to kind of study this system, which is kind of a crude model. But before we study, we can kind of look at what is a little more generalization of that, and that is the Hamiltonian, which is written out here. Okay, so let me try to describe this Hamiltonian. So the second term is already something we have discussed. The first term is a term where you can have interactions between nearest neighbor spins. So this angle bracket ij tells you that I and j are nearest neighbors. Okay, so you could have a Hamiltonian where you could have a nearest neighbor spin interaction. Si and sj are nearest neighbors, and jij is a coupling between them. Now, the way it is written, it tells you that jij is a coupling of these spins which depends on what is the value of I and j. Okay, now that makes the model a bit complicated, because at different lattice sites you could have a different value of jij. Okay, nothing stops us from writing a model like that, but it may stop us from actually getting any meaningful answers, reliable and meaningful answers from this kind of Hamiltonian. So it may be simpler to consider a model in which Jij is j, a fixed number for all lattice sites. Okay, so that is the kind of model that one would want to study, where besides spin interacting with external magnetic field, they have interaction with each other also. Now, there is nothing very special um, about nearest neighbor interaction as far as the full material is concerned. You may, in the realistic system, you may have next to nearest neighbor interaction also, and you may even have next to nearest neighbor interaction as well. Okay, but point is not to kind of get exact interaction behavior of the system, but try to get a model which should mimic the behavior of the system correctly. Okay, so therefore, in most of the cases, one ends up thinking of models with nearest neighbor interactions. Okay, uh, but I should caution you that that does not mean that people have not studied nearest neighbor interactions. Okay, people have studied models with nearest neighbor and next nearest neighbor interaction as well. In fact, in certain special cases, some of these models are exactly soluble also. Okay. Fine. So a simple model, therefore, would be to take Jij to be independent of lattice site and Hi to be independent of lattice site. That's like saying that you have uniform magnetic field for, and this is true for, of course, all nearest neighbors. So this fact would remain that the interaction is still of nearest neighbors, but the interaction strength is independent of which nearest neighbors you look at. Okay, so let's revert back to the original Hamiltonian that we had written down, which is namely this. Okay, and that would correspond to just setting j is equal to 0. Okay, if you do that, then it is easy to write down the partition function, simply because contribution to the energy coming from the second piece in this Hamiltonian is totally independent for each lattice site. So whatever contribution comes from ith lattice site has nothing to do with what contribution comes from jth lattice site. Okay, so you can just write down partition function from, sorry, contribution from each one of them in e to the minus beta h. Okay, now of course at every lattice set you have only two possibilities, either si is +1 or si is -1. So therefore, if you have n lattice site, your partition function just becomes a product e to the beta h plus e to the minus beta h. Okay, now that is kind of a simple object. You can just write that as 2 times cos hyperbolic beta h to the n. Okay, fine. So in this simplified model, in which you are just saying that at every lattice site you have a spin. That spin can take plus or minus one value, and that spin does not talk to any other spin. It talks only to the external magnetic field, and that is it. Okay. If you do that, then you can write down exact partition function for that system, and that is this. Okay. Is that fine? I hope all of you are with me. In case you are getting lost or yes. Can you speak a bit louder? In the interaction term here, well, you can always consider various kinds of boundary conditions. I have not talked about any boundary condition as of now, but you can have a fixed boundary condition. You could have a periodic boundary condition. You can choose any boundary condition in this system. Okay, but what we are interested in is really the thermodynamic limit of the system. So one way to do that is to actually provide periodic boundary condition to the system. Okay. Is that fine? Okay. So here's a kind of partition function for the system. Very simplified version, but nevertheless, let's try to understand what this is telling us. Okay. So first thing is that we can compute free energy. Given that you have exact partition function, free energy can be computed. So here is a expression. F is minus kBt times log Q. Okay. And once you kind of know what free energy would be, you can utilize this expression to determine various quantities of interest. First quantity that is of interest is magnetization. Okay, we are looking at the magnetic system. We want to see whether it generates magnetization or not. Okay, magnetization is determined by asking what is the response of free energy when you change the external magnetic field. Okay, so that is determined by change in F due to change in external magnetic field. Okay, we have 1 over n factor just to kind of ask how each site would contribute to the magnetization. So therefore, there's a 1 over n factor to kind of normalization. Okay, and you can compute this quantity. Okay, now given that Q is kind of, or rather log Q is just log of cos hyperbolic beta h. Okay, uh, you can take a derivative of this quantity and you can easily see that this would give you a quantity which is tan hyperbolic beta h. Okay, I'm sorry, sometimes I write beta, sometimes I write kBt, but it's just 1 over kBt, but it's the same stuff. Okay. Um, so you can find exact formula for magnetization in this particular case. Now, of course, there is no surprise out here. We have simplified model to such an extent that we can really exactly solve the system. But nevertheless, there is something to learn from this thing, this answer. And what we learn from this answer is that the system actually behaves like a paramagnet. Okay, so how do we see this? A paramagnet is a system or is a material where if you apply a magnetic field, then system kind of gets attracted or develops a magnetization which is in the direction of the magnetic field. Okay, so now you look at this function, m is tan hyperbolic h. Okay, so if h is positive, then tan hyperbolic h is positive. Okay, tan hyperbolic is a function which has a form that it is 0 at when its argument is 0, and it is 1 plus 1. It's kind of grows slowly to plus 1 starting from 0 when the argument goes to infinity, and it grows initially grows fast and then grows slowly to minus 1 when the argument goes to minus 1, minus infinity, sorry. Okay, so that is a kind of a tan hyperbolic function, and this relation m is equal to tan hyperbolic h tells you that positive h gives you positive magnetization and negative h gives you negative magnetization. Okay, which is precisely what you would have expected a paramagnet to do. Okay, so in spite of having oversimplified or almost trivial model describing the spin system, at least this model has one feature, and that is that it produces the paramagnetic behavior of the system without much of a work. Okay, so we see that the system has a paramagnetic behavior. But we also notice one more thing, and that is that the system doesn't have any magnetization of its own. Okay, how do we see that? Well, if the system had any magnetization of its own, then if we had turned the external magnetic field off, the magnetization would have remained non-zero. Okay, but that is not the case here, because when H goes to 0, tan hyperbolic H goes to 0. Okay, and in that case the system doesn't have any magnetization. Okay, so therefore the oversimplified model that we looked at today basically contains the description of a system which is something we would call a pure paramagnet. Okay, we want to ask a question: what will happen if we take J not equal to 0? Okay, as soon as you take J not equal to 0, your Hamiltonian goes back to this form, and with each site having spin Si, taking value plus or minus 1, and uniform external magnetic field acting on the system. Okay, this is a model which is called the Ising model. Okay, and what we will do is study Ising model in the next class. Okay. So I think I have brought you to a point where we would be studying this Hamiltonian in the next class. But when J was equal to 0, we have at least managed to see that this Hamiltonian with minus H summation Si manages to pick the paramagnetic behavior of the system reasonably well. Okay. So I think I'll stop here. Any questions? I hope I'm connected.
Yes, you are.
Okay, thank you. By the way, I should mention one thing that I mean, I said it right in the beginning also, that do let Abhay know that you are crediting the course, okay? So that he would know how many home assignments you will have to uh, correct, and have to tabulate the data for evaluation, for the course evaluation. Okay, and also he will get in touch with you about tutorial sessions, which of course are not going to happen this week, but maybe a couple of weeks down the line. Once we have done some reasonable amount of stuff, then we would have some home assignments. Okay, so please do. Abhay is actually there right now in this Zoom session, so you could kind of, if you choose, you could send him a message. This thing. Okay.
So,
Yes.
regarding Friday's class, since you aren't taking GR at 3, could you shift the morning ASM lecture to 3?
I could do that. Yeah. See,
Oh,
the
yeah.
point is that, like, what I see on Friday is that you have like 4 lectures back to back. Okay.
Yeah.
So I think that is a very taxing thing. So you tell me what you find
I mean,
suitable.
it's only 3 lectures if you have removed GR, like back to back. QIC is in the evening.
No, that I agree. What I'm saying is that, like, I I am preparing my lectures anyway. So what I'm saying is the following: that if you find afternoon suitable, we will keep it in the afternoon. I think that is, let's put it that way.
I mean, I would at least.
Okay, no problem.
So can we keep it in the morning for at least this week? This week we can shift it to afternoon.